laboratories, okay? Jonathan here will run the class. So we'll cover the safety aspects first, and then you can crack on with the experiment. Keep your safety glasses on at all times, okay? The main reason being the Dartech Universal Test Machine runs at about 2000 psi in those pipes, okay? So if a pipe was to rupture, you can have some serious damage to your eyes. And the other point being, when you use the Whitney punch, it punches your holes into your materials and a little clip of steel comes out, okay? So if one to flick out, the glasses will protect your eyes, okay? You use this Whitney punch, okay? Keep the gloves on, but hold the handle on the handle area, okay? It's quite a large span when you use it, so the tendency is to grip it there and punch the hole, which leaves you with a nasty pinch in the middle area, okay? You can see that. That's quite painful. Tensile compression machine. It's quite powerful. We've got 25 tons in max load, so don't put your hands in there to retrieve specimens unless Jonathan says it's safe to do so.
A number of elements of the report. There were three sections of the largest number of marks are the description of the methodology, the discussion of the results, and then the competition validation. Okay, so in this particular experiment,
to make these samples, you need 2 bars. You need to engrave it. This is a vernier height gauge. So horizontal. Hold it against this block. Don't push too hard, just enough to give a fine line. Okay? Now I'll make it 15 by 15, just for an example. So the vertical is the one that you will change. All of the samples will have the horizontal center line, and so. We'll do it again for the second plate. Now we get the Whitney punch. We do the same for second sample and second plate, sorry. Then you need 2 washers, 1 bolt and 1 nut. Now you're going to finger tighten them. Now it does matter how you join them together. It does matter which way you put the washers. Now you're hearing the clicking back, it's just telling you it's going backwards. Once it gets to enough force, it will tilt. Making sure that the lower gap in the jaws meets the same amount of gap at the top to make it consistent and equilibrium. So now the sample will run at 0.2 millimeters per second.
when it comes to talking about and looking at the results, what you're going to find is that as your plates, you're particularly interested in the amount of overlap that you put on the plates, with your overlaps less than 12 millimeters, you're going to typically predominantly see that kind of tearing, where the bolt stays relatively at right angles and it just rips through the material. Okay, so that's a tearing failure. You'll see that. The strength, the overall strength of the joint increases. As you put more overlap in there, it increases. But it reaches a plateau. And that plateau is what you're going to determine around about 12 millimeters. And after that, you're going to start to see other modes of failure.
With joints, there's 3 different failure modes. The first one is a tear mode, where the bolt is being pulled out of its hole. Hence why we've got a plastic region right by here. Okay? So that is tear mode. Then we've got flanking, That's when the material is rejecting the bolt and it's being pulled apart. The material, the excess material, is trying to push it away. Then we have coupling. This is when the material is trying to keep the bolt into the material while it's being pulled apart, and this is the strongest form of failure mode because the bolt is being reinforced so it can last longer.
Sure that when you are doing the experiment that you identify which samples have failed in which way. Also when you have the overlap versus ultimate strength of the joint that you put one single line going through the small overlap, I think less than 12. If you put all the points in there, that's fine, you don't need error bars. If you do any averaging from multiple samples you may have, then you need to put an average line and error bars on the other side. I don't mind which one you do. Most people are just putting all the points in. But if you do put lines, and when we talk about the average line, we're talking about just an average line through them. Do one for the tearing mode of failure, and then put another one, which will be relatively horizontal then, for the other two modes of failure. And you'll see that one goes up and one goes steady state. You can't get any stronger. Your force displacement curve. Identify different parts of the curve, whether you think something's elastic, whether there's some slippage, maybe some bolt rotation, when it goes plastic, and when you just see then the plastic response to the material, the ultimate failure load and completely fails. So the best thing to understand that is to quite carefully watch what's happening there with what's going on the screen and take some notes. Yeah, and that's the best way. Then you can go back to your curve and say, well, for this particular example, I followed it all the way through, and I noticed that at this point, if you've got a video camera, video the bolt actually going through the failure, and match that up to what you know is the force displacement curve. The easiest way to understand it. The actual amount of elastic behaviour up to where you get slippage or rotation of the bolt and tearing initiation is up to debate. It's not clear. You won't see a clear differentiation between the elastic zone and the plastic zone. It's not clear. Okay, so there's mixed mechanisms going on during the failure. So when it comes to the validation, computational validation, you've already done the C1 assignment. You've seen the model is a simplification of the real thing, so that you guys can run it on the student analysis. It's not ideal, and I don't recommend anybody tries to match the force displacement curve because you will run into a lot of numerical problems, modeling problems. On this particular time, I know that there are some requirements still left on the sheet, but I allow you to ignore those, right? What I really want to see is more of a qualitative rather than quantitative. Qualitative, look at the contours of the plastic zone, the plastic strain. If you see a plastic strain that represents the plastic failure zone, if you see that connect with the boundary, that's where the tail's going to go through toward that boundary. So I would hope that you'd be able to look at that, put it side by side and say, well, that little hole that's appearing there looks very similar to my plastic failure zone. And that, as far as I'm concerned, is the extent of validation. That is different to the other experiments when you do them. The other experiments you can get quantitative, and I want to see quantitative comparison, but we'll talk about that when we look at the other experiments. References, which is another part of this, you won't be able to get a lot of references for this particular experiment, so I'm not expecting. If you can get one or two, that's great. Okay? That's pretty much it. Any questions?